So let's talk about the graphs of exponential functions. So the characteristics is, the first thing is f of x equal to b power x. So here is b is greater than 0 and b is not equal to 1. These are the characteristics of the following function. Now you have notice that this is a one-to-one function, meaning that when you draw a horizontal line, it only touches one single point on the curve. Next, you have a horizontal asymptote of y equal to 0. The domain stays negative infinity to infinity. Any value is acceptable, but the range is always positive. So remember that the range value is always positive for an exponential function. Now the x-intercept is none, because notice that there is no, it's not gonna cut the x-axis. So y-intercept is 0, 1 for every exponential function. Now the function is increasing, so it goes up if b is greater than 1. It goes down when b is less than 1. But notice that for both sides the point stays the same. 0, 1 is still the same point. It's not gonna move here. So how to graph the function f of x here? First we have to create a table of points. So we have to plot at least 3 points from the table, including the y-intercept 0, 1. And we draw a smooth curve through the points, and we start the domain, the range, and the horizontal asymptote y equal to 0. So let's start with the first one here. F of x here is 4 to the power x. So use a table here and write down 3 values. So we already know the point 0, 1 here. So 0, 1 will always be the first point we'll have to represent. Next we have x and f of x. So let's write down 2 points, -2, 0 and 2. So let's write -1, 0 and 1. So -1, 0 and 1. So for f of x becomes 4 to the power -1, which is 1 by 4. 4 to the power 0, which is 1. 4 to the power 1, which is 4. So the points are -1, 1 by 4, 0, 1 and 1, 4. So 1, 2, 3 and 4. So 1, 4 becomes, so this is 1 here, and 4 here becomes 1, 2, 3, 4. So this is the point 1, 4. Next you have -1, so this is -1, 1 by 4. So this is the point somewhere here. Now combine the 3 points here, and remember not to cross the x-axis. So always just graze the x-axis, but never touch the x-axis. So this graph here represents f of x equal to 4 to the power x. So they're asking us to find the domain. So domain is acceptable across all the ranges. So the domain here is from negative infinity to infinity. The range goes from 0 here. So it doesn't touch 0. So it becomes 0 to infinity. And the asymptote is y equal to 0. So the y-axis itself becomes the asymptote for the x-axis here. Let's talk about logarithmic functions. So after you complete this section, you should be able to convert from logarithmic to an exponential form. You should also be able to convert exponential to a logarithmic form. And you should also be able to evaluate logarithms, use common logarithms, and use natural logarithms. So let's start with the first topic of converting a logarithmic to an exponential form. So a logarithm of base b of a positive number x satisfies the following definition, that y becomes log base bx provided the opposite of the exponential form for that is b power y equal to x. Remember that here what we are trying to find is logarithm basically finds the value of this power. So the exponential power is what the actual value is found as. So if b power y equal to x, we can say that y is, so the x goes here and b goes to the base. So it becomes log base b x. So this is the form that we do. So log base bx, we call it as the logarithm with base b of x, or log base b of x. So the logarithm y here is the exponent to which b must be raised to get x. So basically logarithm is finding that y value in such a way that you end up getting the value of x. So one way of thinking about this is to think about it this way: b to the y is equal to x. So when you want to go towards b power y, so b base to the power y becomes the value of the becomes x, and y, if you want to find the y value, y becomes log base bx. So this is how we can think about y and x here. So use the same principle now and try to convert here from logarithmic to an exponential form. Here it is given as log base 10 of a million is 6. So remember the idea here. So when you want to write the exponential form, so this here is y, this here is b, and this here is x. So the form is b power y equal to x. B here is 10, 10 to the power 6 equals 100 million. So this is how we can write the exponential form. The same thing here as well. So this is y, 5 here is b, and 25 is x. So it becomes 5 square equals 25. Now the same in reverse would be, how would you write 3 square equal to 9? Notice that this is b here, this is y, and this is x. We have to write it as y equal to log base bx. Y here is 2 is equal to log base b here is 3, x is 9. So this is how we can write the exponential form. So use the same principle and write the other two values. Write the exponential form for the other two values. Pause the video and try to solve this problem. Next, how would you evaluate the logarithms based on the values that we have here? Is notice that here, first thing when we want to solve a logarithmic function, first convert it into an exponential form. So we have the form y equal to log base bx. So this is x and this is b. So this is y here, this is b, and this is x. We have b power y equal to x. B power y is 121 to the power y equals 11. So we know that 121 is 11 square. So 11 square whole to the power y equals 11. So 11 to the power 2y equals 11. And we know that 11 power 1 is the same. So exponents at the base is the same. So the exponents will be the same. So 2y equal to 1. So y becomes equal to 1 by 2. So this is how we can solve the value for y. So use the same principle for the next one. So this is b here, again this is x and y. So we have b power y equal to x. So 2 power y equal to 1 by 32. So 2 power y equal to 1 by 32 can be written as 2 to the power of 5. So 1 over 2 to the power of 5 can be written as 2 power negative 5. So 2 power y equals 2 power negative 5. So bases are the same, so the exponents must be the same. So y equals negative 5. So this is how you can evaluate logarithms. And next, let's talk about common logarithms. What is a common logarithm? A common logarithm is the logarithm with the base 10. So whenever we write log base 10x, we simply write it as log x. Remember that whenever we say just log of x, it basically means that the base here is 10. So the idea here of a common logarithm is that if y equal to log x, then 10 to the power of y equals x. So this is the condition that we use for common logarithms. So here they have given us y equal to log of 1 million. So how would you evaluate this? First things, write it as 10 to the power of y. So notice that this is x here. So 10 to the power of y is equal to a million. So a million here can be written as 10 to the power of 6. So 10 to the power of y equals 10 to the power of 6. So the base is the same, so the exponents must be the same. So y equals 6. Now you can also evaluate the same using a calculator. In the calculator you will see two logarithms. One is log and one is ln. Log here represents log base 10. So the common logarithm is log base 10. So if you see the one with log base x, so this is the one that we use when we want to change the base to something else. Now let's try and use a general model. So the amount of energy released from one earthquake was 300 times greater than the amount of energy released from another. So the equation that we use here is 10 power x equals 300. So represents this situation where x is the difference in magnitude on the Richter scale. To the nearest 1000, what was the difference in magnitudes? So to find the difference here, we have to find the x value. So they have given us that 10 to the power x equals 300. So we have to find x. So one way to find x here is to convert it into its logarithmic form. So this is 10 to the power base. So we know that b power y equals to x. So sorry, 10 to the power of y equal to x. Then y becomes log x. The same thing here. For x becomes log of 300. So x becomes the log of 300. So you can always use the calculator and find the value of log 300. So that value is 2.477. So this is the difference in magnitude between the two earthquakes. So this is how we can judge the Richter scale. So Richter scale is a logarithmic scale that shows you the change in the, for example, a Richter scale of 5 is to a Richter scale of 7 means there is a 200 time difference, there is a 10 square difference or a 1000 time difference between the level of earthquake activity that has happened here. Next, let's talk about natural logarithms. So natural logarithms are structures where in place of the base 10 for common logarithms, natural logarithms use the base e here. So we write it as ln x. Ln x represents log base e of x. So if ln of x is y, then e to the power of y equals x. So this is the condition that we use. So remember that e power x and ln of x are inverse functions of each other. So these are inverse functions of each other. Now, how to use these natural logarithms as an example here. You can use a calculator. In the calculator, if you see log represents log base 10. If you see ln represents log base e. So we can think about ln itself as the value to consider. So you can evaluate using a calculator. Just type ln of 300, you will find the exact value of that particular value. So with that, we end our topic on logarithmic functions. Next, let's talk about graphs of logarithmic functions. So we already told you that logarithm is the opposite of the exponential function, which is basically the inverse function. So here, how to identify the domain? We'll try to identify the domain. Second, we'll talk about graphing logarithmic functions. And we will not discuss transformations because you already know transformations from functions chapter. So here we'll talk about graphing the logarithmic functions. So let's start with the domain. So one way of finding the domain of a logarithmic function here is to find the exponential function's value. For example, recall that the exponential function y equal to b power x for any real number x is the domain becomes negative infinity to infinity and the range is 0 to infinity. Now the same here for y equal to log base bx is the inverse of the function y equal to b power x. So the domain here becomes the range of the exponential function and the range becomes the domain of the exponential function. Remember that the domain and range are the exact opposite values of each other. So here it becomes 0 to infinity for the domain of the logarithmic function and the range becomes negative infinity to infinity. How would you draw the graph? The graph here is going to be symmetrical across the origin. So across the origin basically means that we draw a line passing through y equal to x, a diagonal line, and we plot the points symmetrically on the other side. So an exponential function is generally, if it's an increasing function here, a logarithmic function is also going to be increasing, but here the asymptote is vertical rather than horizontal. For an exponential function, you have a horizontal asymptote. For a logarithmic function, you will have a vertical asymptote. So let's try and find the domain here of any given value. First things that we can do here is that we always have to set up the inequality showing the argument greater than or equal to 0. This is the idea behind that, because logarithm values can never be 0 or less than 0. So here the only argument here is x minus 2, so we have x minus 2 greater than 0. So when you substitute the values, you get x greater than 2. So the idea here becomes open interval 2 comma infinity. So this becomes the domain. So for here again, the only value that we are concerned with is x minus 5 is greater than 0, so it becomes x greater than 5. So we can write open interval 5 comma infinity. So this becomes the domain. So what are the characteristics of the parent function here of f of x equal to log x? Here again, it's also a one-to-one function. It has a vertical asymptote of x equal to 0. The domain is 0 to infinity. The range is negative infinity to infinity. Here in general we have a x-intercept, we don't have a y-intercept. Remember that in an exponential function we don't have x-intercept, we have y-intercept, so it's the opposite here. Here the x-intercept is 1 comma 0 and the key point is b comma 1. And the y-intercept is none, because notice that this is a line that will never cut the y-axis. Now it is increasing if b is greater than 1 and it is decreasing if b lies between 0 and 1. Remember that b can never be negative, so b should always be greater than 0. So that's the idea behind the domain here. So how would you draw the function here? First we draw and label the vertical asymptote x equal to 0. Second we plot the x-intercept point 1 comma 0 and we plot the key point b comma 1, and finally we draw a smooth curve passing through those two points, and finally we state the domain, range and the vertical asymptote. So let's start with log 1 over 5 x. So b here is 1 by 5. So we have 2 points, 1 comma 0 and b comma 1. So b here is 1 by 5, so it becomes 1 by 5 comma 1. So this is 1. So 1 comma 0 becomes, so on the x-axis it is 1 and the y-axis it is 0. This is 1 point. You also have 1 by 5 comma 1. So 1 by 5 comma 1 becomes, so on the y-axis it is 1, on the x-axis it is 1 by 5 comma 1. So on the x-axis it is somewhere here 1 by 5 and on the y-axis it's somewhere here. Now notice that here it's b here, so b here is less than 1, so it lies between 0 and 1. So which means that here the graph is going to be a decreasing function, so which means it starts from the top and it goes towards the bottom. So which means that here the graph is going to look somewhat like this. So if it was greater than 1, so if b is greater than 1, then the curve will look somewhat like this. So the idea here is to remember that b value determines the type of curve that you end up with. So we have to remember that this is the decreasing function here. So use the same principle now. So pause the video here and try to solve this problem. They are asking you for the vertical asymptote. How would you find the vertical asymptote here? Is to substitute x equal to 0. So remember that the asymptote here is x equal to 0. So if you substitute x equal to 0 here, you get ln of negative 1, which is going to be invalid. So the idea here is to take up the value that is external to the extract value. So 3 here is the value. So if x equal to 0, what would be f of x here? So the line here itself gives you the answer. So we have x minus 1 greater than 0. So x minus 1, put it equal to 0 and x becomes equal to 1. This here becomes the vertical asymptote. So this is the way we generally find the vertical asymptote. So we take the value inside the log value and equate it to 0. Whatever the value that you get for x becomes the vertical asymptote. So that equation becomes the vertical asymptote. Next, let's talk about the logarithmic properties. So what are the logarithmic properties? We'll talk about product rule, quotient rule, power rule, how to expand logarithmic expressions, how to condense logarithmic expressions, and use the change of formula for logarithms. Now the product rule here basically states that the product of two values under a logarithm is going to be the sum of logarithms of each individual value. So log of mn becomes log m plus log n, provided that b is greater than 0. So how would you take this and split it? So we have log base 3. So we have log base 3 of 24x times 2x minus 5 So we can split it into log m times log n. So notice that 24x can be split into one part. So log base 3 of 24x plus log base 3 of 2x minus 5. Again, we can split log base 3 of 24x again into two parts. We can write it as log base 3 of 24 plus log base 3 of x plus log base 3 of 2x minus 5. So we can also find this value for log base 3 of 24. So what you can do, that equate it to y. So log base 3 of 24. So if you equate it to the exponential form, so 3 power y becomes equal to 24, and then we can find the exact value of y, or you can just leave it at that and end it right here. So this itself becomes your expanded version of this formula here. So use the same principle now and try to expand the value here. Next, let's talk about the quotient rule. So quotient rule basically says that when you divide the two values, m by n, then this value becomes log base bm minus log base b n. So this is the idea here. So how would you split this now? So this becomes log of, you have 5x over 4x plus 3 times 1 minus x. So notice that the above part is m, the below part is n. So it becomes log of 5x minus log of 4x plus 3 times 1 minus x. Here notice that this is two products. Again, we can split that separately. So it becomes log of 5x. Notice that this minus applies to the entire value. So that becomes log of 4x plus 3 plus log of 1 minus x. So we can write it as log of 5x. So when you multiply minus, you get minus log of 4x plus 3 minus log of 1 minus x. So this is the expanded form of this value. So use the same principle now. So pause the video here and try to solve this problem. Next, let's come to the power rule. So power rule basically says that if you have the power of a value inside the logarithm, then the power can come forward. You can write it as n log b log base b of m. So the power can come forward. So for example, here we have log base 5 of x square. So the power can come forward, so it becomes 2 log x base 5. So this is the idea. So try to do the same for ln x square. Now, so let's try and do the same for this one here. So you have ln of 1 by x square. First things first, convert it into a general value. So it becomes ln 1 minus ln of x square. So logarithm of 1, so L log of 1 is always equal to 0. So 0 minus ln x square, so can be written as minus 2 ln x. So this is the one way of finding this value. So here they're asking us to rewrite this value. So how would you rewrite this? We have 2 log base 3 4. So put the power back onto the 4. So you get log base 3 4 square. So we can write it as log base 3, 4 square is 60. So we can write it as a single value of 4 square, which is 60. So use the same principle now and try to solve these equations. So next, how would you expand complex equations here? So when you have a complex equation like this, you have log base 4 of 27x cubed times 3x plus 1 divided by 3x minus 4. So how would you write this one here? Log base 4, notice that this is quotient rule first, so this by this. So log base 4 of 27x cubed times 3x plus 1 minus log of log base 4 of 3x minus 4. So you have log base 4. Again, these are two products, so we can split it into log m plus log n. So it becomes 27x cubed plus log base 4 of 3x plus 1 minus log base 4 of 3x minus 4. Again, we have two parts here, so we can split this again into two parts. So log base 4 of 27 plus log base 4 of x cubed plus log base 4 of 3x plus 1 minus log base 4 of 3x minus 4. So you have log base 4 of 27 plus, here you have x cube here, so the cube can come forward, so it can become 3 log base 4 x plus log base 4 of 3x plus 1 minus log base 4 of 3x minus 4. So this is the expanded version of this value. So this is how you can expand complex logarithmic expressions. So use the same principle here. Pause the video right here and try to expand this equation. Next, let's come to the other property of condensing logarithmic expressions. So where we are doing the reverse here. So here they're asking us to condense this value. How would you condense this first? So we have log base 3 minus log 3 minus log 4 plus log 5 minus log 6. So one way of doing this is to choose the ones that you can easily convert. We have two values that are subtracting each other, so we can take those two values and write it using the quotient rule. So log m minus log n becomes log m by n. So we can write it as log 3 by 4 plus log 5 minus log 6 can be written as log 5 by 6. Now again you have two values that are adding each other, so log m plus log n, so we can write it as log mn. So log of mn is, so 3 by 4 times 5 by 6. So 3 ones, 3 twos, so it becomes log of 5 over 8. So this is how you can condense the equations in reverse here. So here they're asking us to condense this. How would you condense this? First, make sure that there is only log left and no powers left. So you have log base 3 of x squared, so that is there, but here there is 1 by 3, so push it on to x power x plus 1. So it becomes log base 3 of x plus 1 to the power 1 by 3 minus, you have 2 in front, so push it on to the x plus 1 whole square here. So it becomes log base 3 of x plus 1 whole square, again to that there is a square again. So we have log base 3 x square plus log base 3 of x plus 1 whole to the power 1 by 3 minus log base 3 of x plus 1 whole to the power 2 times 2 becomes 4. Now these two values are adding together, so multiply each other, so you get log base 3 of log m plus log n becomes log mn. Mn becomes x square times x plus 1 whole to the power 1 by 3 minus log base 3 of x plus 1 to the power 4. Notice that these two are subtracting each other, so use the quotient rule, so that becomes log base 3 of x square times x plus 1 whole to the power 1 by 3 by x plus 1 whole to the power of 4. So this is your final answer. So this is how you can solve for the final answer. So use the same principle now. Pause the video right here and try to condense this into a single logarithm. So use the same principle again. Condense this into a single equation. Again the same principle. Condense this into a single logarithm. Next, let's talk about the change of base. So change of base formula uses the formula here. We are using log base b. If you have an unknown base, we can convert it into the value of a known base. So log m base b can be written as log m base n by log b base n. So the simpler way we generally do this is either we write ln m by ln b or we write log m by log b. So this is the way we generally find the values of logarithms with unknown bases. So we convert it to simpler bases and find the value. So how would you write log, how would you change log 0.5, sorry, log base 0.5, 8. So we have log 8 base 0.5. So they're asking us to convert it into natural logarithms. So we can write log, notice that the value comes first. So we can write it as ln 8 over then ln the base, ln 0.5. Here, how would you use this and try to convert it to the change of base formula? So we have log base 5 100 can be written as log 100 by log 5. So this is how you can convert using the change of base formula, where we can find the logarithms of values with unknown bases. So next, let's talk about the last concept, exponential and logarithmic equations. So in this section, we'll talk about how to use like bases to solve exponential equations, how to use logarithms to solve exponential equations, how to use the definition of a logarithm to solve logarithmic equations, how to use the one-to-one property of logarithms to solve the logarithmic equations, and finally, solve some applied problems that involve both logarithmic and exponential and logarithmic equations. First, using the like bases to solve exponential equations. Here, the idea here is that if the base is the same, then the power must be the same. So here we have 6 power negative 9x minus 8 is equal to 6 power negative x. So if the bases are the same, the exponents must be the same. So we can equate the exponents. Minus 9x minus 8 becomes minus x. So solve for x. So push this x this side and 8 to the other side. So minus 9x plus x becomes plus 8. Minus 8x becomes 8. X becomes negative 1. So this is the value of x. The same thing for this here. You have 5 and 5, both bases are the same. So the powers must be the same. So 2x equal to 3x plus 2. So push 2x to this side, 2 to this side. So it becomes 3x minus 2x is equal to minus 2. X equals negative 2. So this is how we can find the values. Next, how to use like bases when you have different bases here. So here we have 4 power x plus 2 is equal to 16 to the power x plus 1. But what we can do, what we also know is that 16 can be written in the terms of powers of 4. So 4 to the power of x plus 2 becomes 16 can be written as 4 square to the power of x plus 1. So 4 power x plus 2 becomes, so a power m whole power n becomes a power mn. So 4 to the power 2 times x plus 1. So again, bases are the equal now. Now we can equate the power. So x plus 2 equals 2 times x plus 1. So which becomes x plus 2 equals 2x plus 2. So if you push x to the other side and 2 to this side, so you end up with 2x minus x equals 2 minus 2. So we have 2x, sorry, x equals 0. So this is the x value for this equation. So use the same principle now. Here 25 can be written as 5 square. So pause the video and try to solve this problem. Next, how to solve here. So 5 power x can be written as 5 to the power. Root can be written as 1 by 2. So a square root is 1 by 2, power 1 by 2. So if it is cubed root a, it becomes a to the power 1 by 3. If it is nth root a, we can write a to the power of 1 by a. So next, let's talk about exponential equations using logarithms. So how would you use exponential equations when you have different bases here? So we have 9 power x minus 10 becomes equal to 11. So one way we can do this is to apply log on both sides. So write it as log of 9 to the power x minus 10 becomes equal to log of 11. So we know that power comes front. So x minus 10 becomes x minus 10 times log 9 equals log 11. So x minus 10 equals log 11 by log 9. X becomes log 11 by log 9 plus 10. So this is the value of x. So this is the idea behind how to solve when you have different powers. Use the same principle here now. Again, apply log on both sides. So when you apply log, it becomes log 2 to the power x becomes log 3 to the power x plus 1. So the powers will come to the front. So x will come to the front. So it becomes x log 2 equals x plus 1 log 3. So we have x log 2 equals x log 3 plus log 3. So push x's on one side. So you have x log 2 minus x log 3 becomes equal to log 3. So take x common. You have log 2 minus log 3 equals log 3. So x becomes log 3 over log 2 minus log 3. So this is how we can find the x value. So this is how we can solve using the exponential equations. Now, what can we do when you have a complex one like this? Here, one way we can do this is by applying the base that we have on the same side. So log base e to the power of e power x becomes x. The same thing. So sorry, let me write it here as this way. ln e power x is x. ln 10 to the power of x is also x. So the formula is log base b to the b to the power x becomes x. So if base and the value are the same, then we can write directly as the x value. Now, how do you apply that principle here? First, take down the equation 2e to the power of 6x equals 13. So make sure that there is nothing else on one side. So make sure there is only e on one side. So push 2 to this side. So it becomes e to the power of 6x equal to 13 by 2. Now apply ln on both sides. So you have ln e to the power of 6x equals ln 13 by 2. So ln e power x becomes ex. So write down this value right directly. 6x becomes ln 13 by 2. So x becomes ln 13 by 2 divided by 6. So this is how we can find the value of x. So use the same principle now. Pause the video right here and try to solve this problem. Again, the same principle. So make sure that there is only x left, e left one side, push 10 to the other side, and then apply ln on both sides and try to figure out the x value. Here, so how would you solve this one? So you have 3e to the power 2t equals 7e to the power 2t. So make sure e to the power 2t is on one side. So 3 equals 7e to the power 2t minus e to the power 2t. So 3 equals, take e to the power 2t common out. It becomes 7 minus 1. So it becomes 6e to the power 2t. So e to the power 2t can be written as 3 by 6, which becomes 1 by 2. Again, apply ln on both sides. So ln e to the power 2t becomes equal to ln 1 by 2. So ln e get cancelled. So you get 2t equals to ln 1 by 2. T becomes ln 1 by 2 by 2. So this is how we can find the value using exponential functions on each side. So how would you solve this one here? So this one here involves a quadratic form. So we have e power 2x minus e power x minus 6 equals 0. So first thing that we can do here is take e power x square, write it as this way, minus e power x minus 6 equals 0. So make sure that you equate, so assume first e power x equal to ex. So e power x equal to some value y. Let's write it that way. So you get y square minus y minus 6 equal to 0. Now we have the quadratic form. So use the quadratic form and try to find the value. So we can write it as y square minus 3y plus 2y minus 6 equals 0. So y times y minus 3 plus 2 times y minus 3 equals 0. So we can write y plus 2 equal to 0, y minus 3 equals 0. So y equal to negative 2, y equal to 3. So we know that y is e power x, so we can write e power x equal to negative 2 and e power x equal to 3. Again, apply ln on both sides. So when you apply ln on both sides, notice that this value is not going to be applicable because this is negative, so we can take out the solution. Only use the value that is positive. Now we have ln e power x becomes ln 3. ln e power x becomes x equals ln 3. So the x value for this equation becomes ln 3. So this is how. So notice that always assume the negative value to be of no use, because negative values cannot be found for logarithmic values. So whenever whenever you end up with a negative of a logarithmic value, so that value is non-existent. So we can take out that value. So use the same principle now and try to solve this problem. Next, let's try and solve logarithmic equations by using the definition here. So what is given here? We have 2 log of 3x plus 7 plus 8 equals to 12. So 2 log of 3x plus 7. So 8 can be pushed to the other side. It becomes 12 minus 8. So 2 log of 3x plus 7 equals 12 minus 8 is 4. Now you can take push 2 to the other side. So it becomes log of 3x plus 7 equals 4 by 2. So log of 3x plus 7 equals 2. Now we know that log here is 10 to the power, so push log to the other side. So this becomes, using the definition, remember that the base here is 10, so we can write it as, so 3x plus 7 equals to 10 square. So 3x plus 7 equals to 10 square is 100, so 3x becomes 100 minus 7. 3x becomes equal to 93. So x becomes equal to 93 by 3. So 3 1s, 3 3s, 3 1. So x becomes equal to 31. So this is how we can solve logarithmic equations using the formula for the logarithmic equation. So use the same principle here. They have given 6 plus ln x equals to 10. So ln x can be written as 10 minus 6. So ln x becomes 10 minus 6. So ln x becomes 10 minus 6 is 4. So we know ln x equal to 4. So what can x be written as? So ln is log base e, so we can write x is e power 4. So this is how we can find the value here. So try to solve this problem using the same principle here. Again, use the same principle. So pause the video and try to solve this problem. So next one is one-to-one property. One-to-one property basically states that if the logarithm is the same, then we can equate the value similar to the base is the same and power becomes equal. Here we can write it as, if ln equals to ln, we can write 50 minus L 4x becomes minus 5x. So we can push from 4x onto the other side. So 50 becomes minus 5x plus 4x. So minus x becomes 50, x becomes minus 50. So this is how you can solve the equation. So use the same principle now. So pause the video and try to solve this problem. So what is given here? So log of x plus 12. First make sure that there is only one log left on both sides. So these two are adding each other. So we can use the product rule. So log of x plus 12 becomes log of x times 12 becomes 12x. So log is the same, so the equate the values inside the logarithm. So x plus 12 becomes 12x equals to 12x. So 12x minus 12, x becomes 12, 11x becomes 12, x becomes 12 by 11. So this is how we can solve the problem here. So use the same principle now, pause the video here and try to solve this problem. Now, we can also use the same principles and apply it to problems like half-life. So half-life, for example, here is the formula here is written as e of t equals to a naught to the power of 1 by 2 whole to the power t by t. So where a naught here represents the initial amount, at here, a naught is the amount initially present, uppercase T is the half-life period of the substance, small t is the time period over which the substance is studied, and y here is the amount of substance left after time t. Remember that there is a radioactive decay that happens after a certain time. So one best way of finding how much amount of radioactive material is left is by calculating the actual amount by using the half-life formula. So this is called as the half-life formula. So here they have given us that how long will it take before 20% of 100 grams of samples of uranium has been decayed. So uranium has a half-life period of 703,800,000 years. So they're asking you for 20% to be left. So they are asking you for A of t by A naught. So notice that 20% here means that A of t by A naught is 0.20. So from the formula we know that A of t is A naught times 1 by 2 to the power t by t. So if you push A of t A naught this side, so we get A of t by A naught becomes equal to 1 by 2 whole to the power of t by t. Here we know that t value, so t value is 703,800,000 years. So A naught by AT is 0.20 equals 1 by 2 whole to the power of small t by capital T here is 703,800,000. So 703,800,000. Now how would you find this value here? First, use the logarithm principle here and try to apply log on both sides. So when you apply log on both sides, it becomes log of 0.20 becomes log of 1 by 2 whole to the power of t over 703,800,000 years. So the power can come to the front, so we can write this equation as log of 0.20 can be written as t over 703,800,000 years times log of 1 by 2. So t value becomes log of 0.20 times 703,800,000 years divided by log of 0.5. So use a calculator. So we have 0.2 log times 703,800,000 years divided by 0.5 log becomes, so the total time taken for that to eliminate is t becomes 1,634,172,993 years. So this is the amount of time it takes for 1,000 gram of sample to become 20% of its original value. So which means that 100 grams to become 200 grams, it takes this much amount of time. So this is how we can apply the principles of exponentials towards half-life period problems. So remember the formula, A of t equals A naught times half to the power small t by capital T, where t represents uppercase T represents the half-life and small t represents the total time we are evaluating over. So with that, we end our lecture on exponential and logarithmic functions. I will see you again in the next lecture.